Okay, hello everyone. I'm Ruihua Wang from Tsinghua University in China. Today I will introduce our paper TeSec. I am a third-year master student and I will be graduating from Tsinghua University next month. My co-first author Peng is a fourth-year undergraduate who is also graduating next month. Professor Wang and Professor Zhao are our teachers, and they guided us to complete this paper. Our paper is about accurate attack investigation for web applications. For enterprises and organizations, various web services are often exposed to the outside world. Web applications generally use a browser-server architecture. Users interact with web pages with a browser, which sends requests to the server. This interaction model gives hackers opportunities to launch attacks from their browsers, although some attacks do not pass through the UI. For attacks that require stealth, like APTs, imitating normal user behavior is the most covert way. So the meaning of accurate in TeSec is to trace to the UI element. This topic is meaningful but lack of research. Here we should know that TeSec aims to protect the owner of websites, namely the enterprises and organizations, not the web users. This may be different from some other papers. As a result, some attack skills like phishing is not considered in this paper. In order to trace to web UI elements, server-side method is necessary for TeSec. The reason is very simple. Under the browser-server architecture, if we want to protect the server, then the client corresponds to the hacker's computer, and the information collected from a hacker's computer cannot be trusted. This will cause client-side methods such as JSGraph hard to be used. In addition, client-side methods using timestamp matching algorithms such as UI scope is not suitable for web scenarios because of the high concurrency. For server-side attack investigation, we need to establish a user access model of the website. Enterprises and organizations generally follow the norms of software engineering when developing their websites. One of the most important principles is test-driven development. The test cases includes both back-end test cases and front-end test cases. Front-end testing is to use Selenium or other tools to write scripts so that all available human-computer interactions on the UI are traversed. These test cases are an important data source that has been ignored for a long time. This article will use these front-end test cases to establish a user access model, thereby constructing the connection between UI elements and network requests. This is why this article is called TeSec. TeSec means test and security. Here we will give a motivating example. KLISS is the security analysis of a company. When the IDS system finds a malicious file in the internet, KLISS wants to know through which UI element the malicious file has been uploaded. So she finds the website attendant Bob. When they do attack investigation, they meet two core difficulties. The first one is how to locate the suspicious web request from the audio log of malicious event. And the second one is how to locate the suspicious web UI element from the suspicious web request. Firstly, we will talk about how to find the network request from an audio log entry. When a network request is sent to the web backend, there are three situations. That is, using process, thread, or core execute this request. Actually, multi-process and multi-threads are the same because the process or thread will process request sequentially. The provenance graph looks like dependency explosion, but in fact it is not. When we trace from a syscall to a request, we can firstly partition the log with PID and TID, and then find the nearest web request in sequence. Coroutine is different from process and thread. Some web frameworks use coroutines to execute network requests. Coroutine is a user-level mode. A process might contain multiple coroutines. The unique feature of the coroutine is that it doesn't guarantee the order of request execution. As shown in the figure, request A arrives first and request B arrives later. But in the middle of the execution of coroutine A, the system can switch to coroutine B and then switch back to coroutine A. For the case of coroutines, our solution is to insert a delimiter log into the system every time the coroutine switches. We use a system call that doesn't exist. The audit system will automatically record this syscall when the coroutine switches. For the purpose of logging the coroutine switching, we should slightly instrument the web framework. This instrumentation looks like a monkey patch. As far as we know, most of the attack investigation articles in recent years haven't discussed the coroutine mechanism, so this is one of our contributions. Here are some details about our instrumentations. We use filter mechanism in Tomcat, use ethnic hooks in Express, and use built-in set task factory in Python. By the way, just like many other papers, we modified audit-D to make it support the recording of TIDs. Now I will talk about the second part of TeSec. When we trace to a specific web request, how do we know which UI element causes the request? This is an interesting question. In fact, we find that it can be transferred to a string matching problem. There are many backend APIs in a system, and the number of the APIs is limited. We might regard them as an alphabet. The front end of the site always needs to call the backend APIs. When we press a button on the website, for example, in this picture, I press the Google search button, the browser will send the request sequence to the server of Google. If we regard a single backend API as a character, then this sequence is a string. From the perspective of the server, we receive the string from A to N. From the browser's point of view, we send the string LMNOPQ. We need to guess what string the browser sent based on the string received by the server. In fact, probably when button 2 is clicked, the browser also sends the string KLMNRST. So when the server receives this request sequence, it can infer that the user clicked button 1 or button 2. So there remains two questions. Question 1, how to get the string of each UI element, and question 2, how to implement this string matching. I think you have already known the answer of the first question. The name TeSec means test and security. Actually, we use the front-end test cases here. Because large enterprises and organizations can write enough front-end test cases for the website, we can execute these test cases to obtain the relationship between UI elements and web requests. We made a simple modification to the Selenium framework to automatically support this. We allow Selenium to actively issue 3 commands, start, stop, and finish, so as to separate the request corresponding to each UI action. In this way, we can easily know the string corresponding to each UI element. For the second question, that is how to implement the string matching in this scenario, we use the AC automaton. This is a classic algorithm from 1975. You know, this year is already 2023. We are very proud that we solved this problem using a suitable algorithm invented 50 years ago. Taking these 6 strings as an example, as shown in figure A, each pass from a blue node to the root represents a valid string. In model construction phase, we use these valid strings to model this AC automaton. Then in running phase, the server may receive a string. In this example is CABCA, and the status of AC automaton will move with every character. Finally, the status stops at this blue circle. When we need to query, we will find all the possible strings in this status. In this example, we find BCA, CAA, A, and AB. These 4 strings correspond to 4 buttons. Let's take a look at the complete process of TeSec again. After the IDS system issued an alarm, we traced back to the corresponding web request in step 1, that is, a certain state node on the AC automaton. Note that since this state of the AC automaton will move in real time during the running phase, we will record the current state of the AC automaton in the delimiter log. So in step 2, we directly query the AC automaton to find all legal strings. Eventually, we will output all possible UI elements. Like in this picture, we output 4 possible buttons. Our entire system is divided into training phase, online running phase, and attack investigation phase. The training phase uses test cases to obtain the matching of UI elements and strings. The running phase is continuous. When an alarm is received, we will conduct an attack investigation. The speed of this stage is very fast. We can directly inform the security experts which button the threat comes from, so that they can fix the website's vulnerabilities as quickly as possible. TeSec has done a lot of experiments. I only introduced 2 of them here. We did a comparative experiment with UiScope's timestamp matching strategy. Obviously, the strategy based on timestamp matching on the client will have a significant decline because of the high concurrency of web applications. Moreover, when the attack script uploaded by the attacker sleeps for a while before starting, the timestamp matching strategy will be completely unable to use. The method used in TeSec will not be affected by these factors. In addition, in the example just now, we recommend 4 buttons to the security experts. And we also counted how many buttons we generally recommended to users in some applications. It can be seen in the figure that in most cases, the number of buttons we recommend doesn't exceed 2. That is to say, our results are accurate enough to help them locate the real problem. Finally, I will summarize the contribution of TeSec. Firstly, we noticed the importance of UI level tracing for web applications and proposed this question. Secondly, we give an interesting solution leveraging front-end test cases. We design an audit log partition technique under high concurrency to precisely match system calls and web requests, and use AC Automaton to effectively model the relationship between UI elements and web requests. Thirdly, we implement TeSec for mainstream web frameworks such as Tomcat, Express, and Python. Furthermore, we have already made our implementation open source. As a graduating master student, I'm very happy to have this chance to share my paper in SNP. If you have any questions, you can ask me right now.
Thank you very much. Questions indeed. Maybe I can get started. So yeah, very interesting work. So essentially, part of the approach is training using Selenium, as you mentioned. I was wondering how you deal with challenges for high-quality training. You have dynamic execution, you have events, you have form submission. So how do you deal with those challenges?
Yeah, we use Selenium to train in our training phase, and we get the matching between UI elements and the AC Automaton in this training phase. In fact, web has web has the high concurrence, yeah. But in the training phase, maybe the concurrency is not very high, but in the running phase, the concurrency is relatively high. So maybe we deal with this problem in our log partition part. Yeah, in the first part of this paper, we deal with this problem. Yeah.
Okay, maybe we want to see if there are other questions. Yeah, let me ask you about the focus of your work is very much on the forensics, right? You know, okay, something had happened, and you have a nice framework trying to kind of roll back to see what has caused it. But since you have already built the infrastructure for dependency analysis, I was wondering if you could also use the framework for discovering attacks and actively looking for vulnerabilities. Essentially doing something what web scanners typically do, having injection tokens and using your framework to see where it would end up in the back end.
Yeah, I rarely mentioned the problem of dependency explosion, but we do not use this framework to find some vulnerabilities in the back end, because we should get an entrance of the attack. And when we get this entrance, we will use this framework to do the attack investigation. Maybe we can use this framework to do some detection work, just like intrusion detection, and to find some vulnerabilities in the web service. But maybe yes, maybe it can be in the backend. But I think maybe the vulnerability will exist in the front end. Yeah.
Okay, thanks very much, Ruihua. Thank you again.